Okay. Hello, everyone. Just before we start, two things. First, just a reminder for everyone, today is the deadline for the PST, right? So remember to submit in time, within the deadline, okay? On Turnitin. If you have any trouble with Turnitin, doesn't work, whatever, you send me an email with the assignment, okay? That said, another thing, pulse results. Thank you very much for completing the pulse. Overall, quantitative result was quite good. 4.1 is considered a good result for Q3, which is the overall question, and seems like we're doing okay. So thank you very much for your comment. I'm happy that you kind of appreciate the unit. Main positive comments I just summarized. Of course, there were many comments. I cannot put them all in this slide, but I summarized the more common and recurrent. So positive comments about lectures and tutorial. Thank you very much. That's not sand, it's and. To improve too fast works example in lectures, somebody said too fast works example and too short tutorials and more order in Blackboard. I'm not exactly sure what that means, but someone said that, very many people actually, well, one or two, probably one, that said that the stuff on Blackboard was not properly organized. If you have more precise thing of how you would like Blackboard or some suggestion, we're really open. I thought it was quite structured. I mean, lecture is in lecture and tutorial is in tutorial. But if there's anything that can be done better, let us know. That's a quick win. I mean, to just change the order of stuff in Blackboard is pretty easy. Too fast works example in lecture and too short tutorials, that's a bit more difficult to change. Definitely I will try to slow down. Well, it's my last lecture today, but I'll tell YT to slow down, to go slowly with the worked example in the class. For the tutorials, it's already 1 hour and a half, which is quite an exception. Usually they are 1 hour, the tutorials, standard. So we achieve 1 hour and a half. It's tough. I don't think we'll be able to get 2 hours tutorials. What we can do is do less exercises and go slower, if that's, do you think it's a good idea, or it's, what's your opinion on it? Who's for many exercises done at the current pace? So many means 4 or 5 usually. You can raise your hand. Who's for less exercise, say 2 or 3, but done slower? Okay. Seems that the majority prefers current situation. It's always a balance, I understand that. What we've done in the past to try to mitigate this problem, so if you go, the problem is that we have 1 hour and a half. If we go too fast, if we go too slow, we do many exercises, we do few exercises, and we do them in detail so you're sure you get 100% of it. But on the other hand, maybe we don't show you all the possible type of exercise you can face. If we go fast, we show you many, but then maybe you miss some step. For that reason, what we did, we went for the for the medium version, like 4 or 5 exercises. But there are videos on Blackboard. So on Blackboard, I've always advertised them. There are videos recorded of solution of exercises. These go with your own pace because you can pause them and play. Okay? So that's what we tried to do. If you have any other suggestion, we're really open to do better here. It's tough with the constraints we have. Anyway, thank you very much for the participation. Please participate as much and even more numerous in the insight at the end of the semester. It's very important for us to know what you think about the unit and for QT to know what you think about our unit and in comparison to other units and how does it fit, how is it done, etc., etc. Okay? Thank you very much. Now, let's come back to vibration. Let's start with an example to recap what we did in last lecture. What did we do in the last lecture before we start this example, actually? what did we see in the last lecture? We've seen 3 vibrations, right? The vibration of a body without a force. So I hit this thing and I see how it vibrates. Okay? That's what we've seen last time. What have we seen? Which are the most important parameters in vibration? Important. Natural frequency is one. Another one. Another one very important. Sorry? Mass is, yes, it's important, but it's part of the whole thing. It doesn't really relate to vibration directly. The amplitude is important, but it depends on initial condition. There's another property of the system which is very important in vibration. So one is natural frequency. So this system has a certain natural frequency, meaning if I hit it, it will vibrate with a certain frequency. Damping ratio. So damping ratio is very important because it tells you which kind of free vibration you have. Okay? If damping ratio is equal to 0, which kind of free vibration do you have? Undamped, which means it's going to be a sine wave and last forever. So you hit it, and that thing is going to go forever. That's obviously not very realistic. So the next step is if damping is little, so the damping ratio is between 0 and 1, what happens? It's underdamped, and what happens to the system? Exactly. It's a sine wave, so it's still, there is a sine wave inside the formula, so it still oscillates, but there is also a negative exponential, which makes that oscillation fade away in time. Okay? What happens if damping is equal to 1 or greater than, damping ratio is equal to 1 or greater than 1? Exactly, critically damped or overdamped, which means that the vibration basically doesn't happen. It doesn't oscillate. It just goes back slowly to the equilibrium position. Okay? It moves back to the equilibrium position without oscillating. Good. So basically the idea is that when you have a system, the first thing you do, you can calculate with the system itself without knowing anything about forces or initial condition or anything. You can immediately calculate natural frequency and damping ratio. That tells you a lot about how the system responds to whatever you do to it. Is it clear? So amplitude depends on how much I hit it, how strongly, obviously, right? If I hit it very little, the amplitude would be little. If I hit it strong, it would be a lot. But natural frequency and damping ratio don't depend on what I do to the system. They're going to be the same given the system. That's why you can immediately calculate for this system what's the natural frequency, what's the damping ratio, without knowing anything about what you do to the system. That tells you a lot about how the system will respond to whatever you do to the system. Okay? And today we see actually forced vibration, and we see that these two quantities, natural frequency and damping ratio, will have a very important role also when there is a force. Okay? So before seeing the forced case, let's recap with this exercise. So we have this system. We want to know what's the natural frequency, damped and undamped, the damping ratio, and the type of vibration. And by that I mean undamped, or underdamped, overdamped, blah, blah, blah. And qualitatively draw the vibration profile in time. Why qualitative? Why can't I draw it perfect? Any idea? What do I miss there in this system? Which information am I missing to draw the actual exact vibration profile in time? The initial condition. Without initial condition, I don't know the amplitude. It depends how much I pull it at the beginning, basically. Right? I don't know the amplitude, I don't know the phase. So I cannot draw it exactly, but I can draw the shape of it because I know if it's underdamped, overdamped, undamped, blah, blah, blah. Clear? That's the idea of the exercise. Okay, I'm copying on my piece of paper the data. Okay. So I want to find omega n, zeta, omega d, and the type of vibration. How do I do that? What do I start with? It's a dynamics problem, so I always start with free body diagram. Okay? So let's draw the free body diagram of that mass. Okay? So I have damper force, the damper force going towards the center of the damper, and C delta L dot. Then I have K delta L. There's no space. I'm going to draw a line just to draw the other forces. C delta L dot, the other damper. And then mg. This line is just because I have no space here. They're going to be all here, obviously. Okay? Any other force? Any other force? No. That's it. Now, let's draw a reference system and our little motion. So I assume that delta static has gone in which direction? Where do you think the mass has gone from unloaded spring to equilibrium position? In which direction has it gone? Down, right? So if I put the mass, I remove the mass, I have this spring there. If I put the mass there, this is going to settle downwards, right? Because of gravity. So delta static is going to be in this way. While then that reaches the equilibrium position, and then from the equilibrium position, I have y. Oops, I should have drawn it dotted because it's not a force. It's just a reference for me. Now why I draw it positive upwards because, well, that's how we usually draw y. Good. Next step. Newton's law. So mass multiplied acceleration equal the sum of all the forces. These are all the forces. They're all negative because they go in the opposite direction with respect to y. So minus 2c delta L dot. I wrote 2 because I have 2 of them, so I just put them together in a single expression. Minus k delta L minus mg. 1, 2, and 3 forces. These two, as I said, I put them together because they have the same magnitude as just double. Everybody agrees? Any question here? Okay, next step is to express these delta L's. So how much is delta L? So delta L is the deformation of this spring from when it's unloaded. So when it was unloaded, first thing, it has moved by a certain delta static. Agreed? And that motion did compress the spring or extend the spring? Compress. So minus delta static, because every compression is negative. And then from that position, the mass moves by a certain amount y. That amount y does, if positive, does extend k, does extend or compress the spring? Extend, see, it's going that way. So plus y. Okay? Any question here? Okay. Delta L, we have it. Let's check delta L dot. That's pretty easy. It's the derivative of this. What's the derivative of this? In time. What's the time derivative of that quantity? Y dot. Why is that? Because delta static is a constant, so when you differentiate, it goes. Y, the derivative in time, is y dot. Now I can substitute this expression into here, and I obtain y dot. I bring those on the other side, just plus 2c delta L dot is y dot, plus K, delta L is this thing, plus mg equals 0. And that's my equation of motion. What do I do with it? As usual, I first impose equilibrium. So at equilibrium, what happens? At equilibrium, y dot dot equals 0, y dot equals 0, and we chose y so that y is equal 0. Therefore, this goes to 0, this goes to 0, this goes to 0. I'm left with minus k delta static plus mg equals 0, which gives me delta static equal mg over k, which is equal, well, m is 10, g is 9.85, so 9.81, so 98.1 divided 1,000 is 0.0981 meters, if I'm not mistaken. Okay? So I know that because of gravity, this mass has settled basically almost 10 centimeters downwards from unloaded spring position. So if there was no mass, the spring would have a certain length, which would be 9 centimeter, 0.8 longer than what it is when you put the mass on top of it. Okay? Clear? That's the delta static. Good. We weren't actually interested in that. We are interested in omega, zeta, and omega d. Omega n, omega zeta, and omega d. So now that I have this, I can chuck it back in, and I know that this term will eliminate this term. Let's do it just because we are not trusting people. Now I substitute this delta static. It's mg over k plus mg equals 0. Obviously, this term, mg divided by k multiplied by k, is mg negative, which goes with this term. So I'm left with my dot dot plus 2cy dot plus ky equals 0. Questions? Good. Now, everything in front of y dot dot is m star. In this case, is equal to m, which is 10 kilos. Everything in front of y dot is called c star, which is equal, in this case, to 2c, which is 10. Everything in front of y is k star, which in this case is equal to k, which is 1,000. Once I have these three numbers, basically I'm almost done. Because omega n is going to be square root of k star over m star. 1,000 divided by 10 is 100. Square root of 100 is 10. Zeta is c star over 2 m star omega n. C star was 10 divided by 200. 10 divided by 200 is 0.05. And finally, omega d is square root of 1 minus zeta square omega n, which is, I did the calculation before, 9.987. So this system is which type of vibration? Underdamped. So I have that, oops, zeta is between 0 and 1, and therefore is under damped. Okay? Now the last thing which we are left to do is qualitatively draw the vibration in time. We don't know the initial conditions, so I just draw them randomly. I know that the system is going to vibrate like this because the expression x, sorry, it's not x, it's y. Y of t is going to be equal to a certain amplitude, e minus zeta omega n t, sine omega d t plus psi. So I know it has an exponential, which makes it decay. I know it has a sign, which makes it oscillate, a certain amplitude and phase, which I don't know. And I know that this is period t equal to pi over omega d, which is equal 0.629 seconds. Okay? Any question here? In this case, I cannot find the amplitude because I don't have the initial conditions. Okay? You see that this kind of vibration is exactly this kind of vibration. It oscillates and then it becomes smaller and smaller. Exactly that, like that drawing there. If I plotted this vibration in time, it would look exactly like that one. Is it clear? It oscillates, but it dies out. Okay. So today, we see what happens when we add a force. That's obviously a more relevant case than the free vibration, right? In reality, if you look at mechanical systems, they usually have forces. They have stuff moving. They have motors. They have stuff, okay? Even structures undergo certain forces, right? Like earthquake for a building, wind for a building, whatever, okay? And we will see why we did the free vibration case, why that's relevant actually also for the force vibration. So, simple case there. Imagine we have a mass, like the one we've seen so far, supported by a spring and a damper. That will have a certain delta static and a certain vibration y. That mass, instead of being free to move, has a certain force, which is a certain magnitude. This F0 is a certain amount of newtons, say 5 newtons, 4 newtons, multiplied by a sine wave. What does it mean? It means the force looks like this in time. So first it pushes up and then it pushes down. Okay? So imagine a force that does this. Okay? So when I push up, the force is positive. When I push down, the force becomes negative. So imagine I have a force which does this and then pushes down, then up, and then down, okay, with a sinusoidal time profile. Is it clear? This force will generate a vibration, obviously. I mean, if I shake this thing, that will vibrate. Okay? If I do this, that will vibrate. Clear? Any question on this concept? So how do we solve it? Well, we do free body diagram. So we take this system. I do free body diagram. I have my usual forces plus this external force, which vibrate. I write Newton's law, and I obtain what I've obtained before with this force. Okay? Clear? Now, what happens at equilibrium? At equilibrium, obviously, again, y equal to 0, y dot equal to 0, y dot dot equal to 0. Do you think there's going to be an equilibrium if I keep the force there? So if this force is shaking, will the system stay there? No. So to have equilibrium, I also have to remove that force, this sinusoidal force, otherwise the system shakes. So I remove also this force. I remove y dot, I remove y dot, and I remove y because I've chosen a smart coordinate system. And I'm left with the same equilibrium position as I have without the force. Okay? I do the same, I also remove that force, basically, so I obtain the same equation as before. Okay, fine. I substitute before, this one I substituted back in. That will cancel out with our mg as it has done before in our exercise. Right? So I'm left with this equation. Before, you remember, we were left with this equation equals 0. Now we have this equation equal a certain force function. Okay? How do we solve that equation? What's the solution of that equation? Any idea? You've seen second-order ODEs, ordinary differential equations. And you should know what's the solution to this type of equation. Any idea? Very good. So let's do a step back. That's the final answer. What's the difference between this equation and the equation we have seen for free vibration, which was, I don't have it here. I'll rewrite it. Oops, oops, oops. Here. So this was the equation we have found now. The equation we were finding for free vibration looked like this, right? This was the equation we had before. This is the equation we have now. What's the difference between the two? This is called a homogeneous ODE. This is a non-homogeneous ODE. The homogeneous thing means that there's nothing which is not dependent on y. Okay? Homogeneous ODEs are ODEs where all the terms have y or its derivatives, like this one. There's nothing else which has, nothing which doesn't have y, okay? Which doesn't have the solution in its expression. In this equation, we have this term which doesn't have any y, and that's why it's a non-homogeneous ODE, okay? Good. Now, the solution of this type of equation is given by the sum of two solutions, of two y's. So the actual vibration y, it's going to be the sum of two functions. One is called the homogeneous solution, and one is called the particular solution. The homogeneous solution is obtained solving this equation without this term. So how will it look like, this YH? Any idea? So YH, this component of the vibration, is obtained by solving this equation without this term, so basically this equation. So what's going to be like this YH? Which kind of function is it? Any idea? YH of t, how does it look like? Well, it looks exactly like the free vibration, because it's exactly the same equation. So this thing is going to be either undamped and therefore a sinusoid, underdamped and therefore a decaying sine wave, or critically or overdamped and so simply something that goes back to the equilibrium position. Clear? So this YH is basically the free vibration expression is the same. Okay? So if it's underdamped, YH is going to be a certain amplitude E minus Z omega nt sine omega dt plus psi, the usual expression we've seen so far. That's YH. What about YP? That's the new one. That's different from the case of the free vibration. Luckily, that's much simpler. YP looks like the force. So if the force is a sine wave, it's going to be a sine wave. A sine wave with the same frequency, actually. You don't even have to find the frequency. The frequency is going to be exactly the same as the one of the force. It's only going to have a different amplitude and a different phase, where the amplitude has this expression and the phase has this expression. Clear? So we have that y is going to be the sum of this function, which looks exactly like the one we've seen in the free vibration, and this function, a certain number multiplied by sine. Is it clear? And the sine will have the same frequency of the force. So if the force is shaking 1 cycle per second, that thing is going to vibrate 1 cycle per second. Okay? With this part of the vibration is going to be at 1 cycle per second. If the force is at 3 cycles per second, then this yp is going to be a vibration at 3 cycles per second. The only thing that's going to change is the amplitude and the phase. So maybe it's happening a bit later than the force because the phase is not 0, and y is the amplitude. So if the force is 10 newtons, maybe this vibration is 5 millimeters. I don't know. Depends. Moreover, this y, we can find it with this expression. So before we look at this expression, let's have a look again at one of the most common type. So we've said that in mechanical system, very often, zeta is between 0 and 1. So YH, which has exactly the same shape as the free vibration, will be this. This is the free vibration for zeta between 0 and 1. Agreed? Good. Yp, instead, we've said, it's a function which looks like the force, so it's a sine wave with the same frequency, a certain amplitude, and a certain phase. Okay? Good. Let's forget about this for now. These terms, more or less, we know how to find omega d, omega n, and zeta. We know that we need to use initial conditions to find A and psi. For now, we keep them there. Now, let's have a look at how this thing looks in time. How does a function like this look? Any idea? It's pretty complicated, right? It's not very simple. How does it look like? How would you draw that function here? Can you draw this function? This part, yp, can you draw it? Well, it's pretty simple. It's a sine wave. So it's going to be a sine wave. Can you draw this? We've drawn it 5 minutes ago. So you can definitely draw this. Can you draw the sum of the two? Well, if you have a bit of drawing skill, you can. It's a bit, basically you have to sum the two. And I'll show you how it looks like. So the blue one is the homogeneous solution. This one. We've seen it before. All right? The red one is the particular solution. It's simply a sine wave. You see, it's a sine wave. The sum is the blue one. Sorry, the black one. The black one is the sum between this and this. So this point plus this point, give me this point. This point plus this point, give me this point, and et cetera, et cetera. Okay? Point by point sum. Now, what do you notice about the black one? What's the interesting characteristic of the black one versus the blue and the red? Any comment on the black one? Exactly. And why is that? So, sorry, I said to all the class if they didn't hear. So after just a short time, let's say 1 second exaggerating, being very picky, the black and the red are basically exactly the same. Why is that? Sorry. Exactly, because the homogeneous part is gone. Does it always happen? Yes, it does, because we know that undamped doesn't exist in practice. There's always a bit of damping. So your homogeneous solution, it's going to go. Maybe after a long time, if damping is really little, But after a while, it's gone. It has to go to 0. Do you agree? That homogeneous part is like free vibrations. We know, except for undamped case, they all go to 0 after a while. And we know that undamped case doesn't exist in practice because there's always some damping. Try to hit whatever, it will never vibrate forever. Okay? Good. So that's why the particular solution is also called steady state vibration. Because except for the initial part, that's how the vibration looks like. It's basically yt equal y sine omega t minus phi. Okay? So this is the real expression of the whole yt, but this part goes to 0 after a while. So you know that after a while, this is the only component left. Clear? It's very important. So often, we neglect this part because we know it goes away after a while, and we concentrate in finding this. Is it clear? Now, what's the most important number in the whole equation then? In this whole equation, what's the most important number? We have a lot of numbers there. We have A, zeta, omega n, omega d, psi, y capital, omega capital, phi. Which one of all those numbers is the most critical? Omega capital. So let's say which one are not probably so interesting. They're interesting, but they're not the most important. A, is it the most important? Why not? Well, we said this part disappears, the whole lot. So yes, it's important at the beginning, but after a while it's gone. So who cares? Zeta, omega n, omega d, psi, all this part goes away. So apparently, at least directly, these terms are not so important. Now we are left with 1, 2, and 3. You have this system. And it's forced, so it starts vibrating. Which one is the quantity you are more afraid of? Capital omega is one option. What about phi? Is it interesting? Nah, not really. Phi tells me only if it's delayed a bit or anticipated a bit. It's not really critical. Yeah. What about capital Y? What does it tell me? How large the vibration is. That's definitely interesting. So these two, I would actually give priority to this guy. So first of all, I want to know if this thing vibrates so much that it hits here. I mean, it's unlikely, but okay? The omega will tell me how fast it vibrates. So it will have an effect on a lot of stuff. But Y gives me the amplitude of vibration, so it's very, very critical. Luckily, we have an expression for Y, which is this one. Now have a look at that expression. I don't want to distract you. Have a look at that expression. How is Y, what is Y affected by? So if, what is F0? F0 is the magnitude of my force. Force is variable. It goes from minus F0 to plus F0. It changes in time. But the maximum value is F0. So that's how big is my force, basically. Of course, bigger force, bigger vibration. Well, I would expect that. This is divided by stiffness. So the bigger the stiffness, the smallest the vibration. Does it make sense? Well, yes. If it's very rigid, I can push, but it won't move much. However, so this part is pretty obvious. The top part is pretty obvious. Actually, if you had that F, instead of being F0 sine omega t, it was simply F0, so a constant force, how much would be the displacement? It would be exactly F0 over k. So this numerator here tells you how much is the displacement if F0 was a constant force instead of being a, sorry, if F was just F0, not F0 sine omega t. Clear? So for when you have a constant force, you would have a displacement equal to capital Y F0 divided by k. And that's the numerator of this equation. It simply tells you, well, if you have a stronger force, it will move more. If you have a stronger spring, it will move less. This denominator is instead affected by the fact that this force is a sinusoidally variating force. It's not a constant force. It's a force that goes like this. This effect is taken into account in this denominator here. And look at the denominator. What have we said about damping in many mechanical systems? There is little, right? This zeta, we expect it to be pretty tiny, like 0.01, 0.05, 0.0 something, very often. So this term, it's likely little. Agreed? Because this number is little. Clear? Good. So let's focus, let's neglect it. Let's say it's almost 0, and let's focus on this term here. When do you expect to get in trouble? So what does it mean, trouble? Trouble means big Y's, okay? When this number is big. This number is big, you're in trouble because you have big vibration. This thing is going to vibrate up and down a lot. So which omega capital will give you a big Y? Have a look at that formula. Exactly. If omega is equal to omega n, this ratio is equal to 1. 1 minus 1 is 0. Square, square is still 0. So this whole thing is 0. We said that this guy is small. So any number divided by a very small number, because this is small, will give you a big Y. Okay? So that's why omega n is a very important term also in forced vibration. We found omega n for free vibration. You remember before at the beginning. But it's also important in forced vibration because if the frequency of the force is equal or close to the natural frequency, you obtain big vibration even if the force is little. So even if F0 is little, okay, if this is close to this, you tend to have very big vibrations. Clear? That's resonance. That's an effect called resonance. When you push the, forgot the name. This thing kids go on, and they swing them. Swing, swing. Yes, sorry, I'm tired. When you push a swing, if you push with the right frequency, you don't have to push much to make it go bigger and bigger and bigger and bigger, right? Because you push with the natural frequency of the swing. Your force has the same frequency as the swing would have if you simply drop it. If you drop the swing, it will vibrate with a certain natural frequency. And if you push it with the same frequency, that swing will grow and grow in amplitude without you putting too much effort into it. Is it clear? Cool. Let's see if I still have this stuff. Yep. So when omega is equal to omega n, you end up with this divided by this. This is equal to this, so it's 1. It's basically this divided to zeta. So it's only damping that keeps things in the realm of finiteness. If damping was 0, in theory, it would have infinite amplitude of vibration. Damping is luckily never 0, but it can be really, really tiny. So this number can go very, very big when omega is equal to omega n. Okay? And that's called resonance, very high amplitude vibration. When omega is much smaller than omega n, what happens? If this is much smaller than this, what happens? Well, this is negligible. It's much smaller than 1, so this is basically 1 minus a number which is almost 0 is going to be 1. This number is very tiny because this is almost 0. This is already small. When I multiply small by small, it becomes even smaller. So what I'm left is basically with this 1. This 1 dominates here. And so y is equal f0 over k. So the amplitude of vibration is the same amplitude you would have if you would push this with a constant force. So if I push this with a constant force, I have a certain amplitude. Okay? If I push with a constant force, that's how much it moves. Now, if I pushed very slowly with the same force but varying force, the amplitude of vibration would be the same as the one I have with constant force. That's the concept. It's called quasi-static because it's not static. This thing varies. But the amplitude of vibration, the maximum vibration, is going to be equal to the displacement you would have if you pushed that system with a constant force of amplitude f0. What happens if omega is massive? Let's say that the natural frequency is 10 radians per second, and I'm shaking with 1,000 radians per second. Any idea? Well, let's try. Look at the formula. Use the formulas to find results. If this is much bigger than this number is going to be much bigger than 1, correct? Let's say this number is 100. Now, this 1 will do very little to 100 square. So this is still a huge number. This is also a big number, or maybe still a quite big number. Smaller than this, probably, because zeta is smaller. But anyway, this whole thing will be a great big number because this over this is big. We said if, that's wrong. If omega is much bigger than the natural frequency, then this number will be huge, making the whole denominator huge. And therefore, huge denominator, even if you have a big force, this will be little. Okay? So it's almost no displacement. I'm going to try. No, this is too high natural frequency. I cannot shake it so fast. Let's see this. What's the natural frequency of this? That's a slow natural frequency. Oh, I can do that. Okay? Oh, this has tons of natural frequencies. That's doable. C doesn't move much. I'm moving very fast. If I move the same force, I'm kind of tired. I'm moving quite strong force. If I move with the right frequency, and I'm not putting almost any force, but I'm the right frequency, I'm shaking exactly with this frequency, which is the natural frequency. Clear? If I go very slow, this will move as much as I would move with a constant force. So it will move here. Clear? The effect of the phase is just that one. So the two, imagine the blue signal is the force, and the red signal is the displacement. Okay? There's no number here because it's just an example. Who cares? So if this displacement has the same amplitude as this displacement, but a different phase, what will happen is that simply it happens later than this, or earlier. But the amplitude is the same, the frequency is the same. So that doesn't change much, the condition. That's why phase often not really important. Okay? Time? Ooh, it's very early. Let's make this exercise. No. Let's play with this first. Then we take a break, and then we do the exercise, and then we go home a bit earlier. Okay, let's try. Aha. Apart from the fact that it's upside down, it's not too bad. People at home will have an opposite reference system than people here. So please multiply everything you see for -1. Okay. This object here has an eccentric mass. There is a mass which is not in the center. So when this thing rotates, it creates a force that shakes upside down. Clear? So this, imagine this. Imagine a force applied here that goes upside down, whose frequency, whose capital omega, I can play with. I have this knob which decides that frequency. The natural frequency of this system can be found simply by hitting it. Now, I'm not sure how much, but I'd say it's definitely more than 1 hertz, more than 1 cycle per second, okay? Because it's definitely faster. I'm not sure how much. I would need to measure it if I need to. Let's turn on the thing, okay? So I go with very 0 speed for now. Let's see if we see it. Ooh. I turned on the wrong thing. Started rotating. You see that thing on the back, you see it on the screen. That's the one generating a force. You see it's not centered, so it generates a force. Very little frequency. I have almost no vibration. Now I start vibrating. You can see a little movement there of the bar. I go up. Now I have a decent movement of the bar. Not much. Why? The force is very little. It's much smaller than me hitting the thing. Now if I go up and I reach a frequency which is close to the vibration of the thing, you see that it vibrates a lot. That's resonance. I'm exciting with the same frequency as the natural frequency of the system. When I hit it before, it was vibrating exactly with that frequency. Now you see how much it's vibrating, even if the force is pretty tiny. Okay? That's resonance. Now I go up. I put a bit of damping, just to let the homogeneous go away. It's vibrating less than before. I've passed resonance, so it's vibrating less. Okay? Because only in resonance you have that omega over omega n equal to 1, canceling out with that -1 you have in the formula and giving you that 0 at the denominator, making big numbers. Clear? Both below and above, you don't have that. Turn it off. So what's the key message here in practice? Why would you do vibration study for a machine? Say you have this machine here. Why would you do a vibration analysis? Why would you even calculate the natural frequency of that machine or the damping or whatever? Exactly, to make sure that, and I'll be even more precise, usually machines operate at a certain speed, right? I mean, think about a turbine or an engine. They have something moving, correct? That something moving creates forces very often. So those forces, which frequency would they have? Well, the frequency at which the thing is moving, highly likely. Okay, so your speed of rotation, radians per second, of your shaft or whatever, your gear, whatever, will likely create a force with the same frequency. Okay? So what you want to avoid is that that frequency is equal to the natural frequency of your machine. Clear? So imagine you have a turbine. You do your analysis. It comes out that this big turbine is a big mass installed on a big platform who has a certain stiffness. And that turbine plus the stiffness has a certain natural frequency, let's say, of 50 hertz. Now, you're generating electricity in Australia, so you need that turbine to rotate at 50 hertz. When the turbine rotates at 50 hertz, some forces will be generated at 50 hertz within the turbine. Your turbine will go upside down a lot. Okay? Up and down, and then upside down probably if it goes too much. Clear? So that's the problem. So actually, that's just a little anecdote. What they usually do is design turbines. They have to rotate at 50 hertz. There's no way, right? I mean, you cannot, okay, my turbine has 50 hertz. I generate electricity at 70 hertz. then there's a problem because you attach your vacuum cleaner, it won't work or something like that, right? So 50 hertz, everybody has to build turbines that operate 50 hertz, at least in Australia. So what do? You design the turbine so that its natural frequencies are all above 50 hertz. Turbine have more than one. In this case, we've seen only 1 degree of freedom system with one natural frequency. But let's say the first natural frequency of the turbine needs to be above 50 hertz, so you're sure you're never, even when you turn it on and turn it off, you never pass through that resonance. Okay? Now, the problem is that usually, it's good practice is more or less at least 20% margin. So let's say if you're operating 50 hertz, 20% is 10 hertz. So you set the natural frequency about 60, and you're going to be fine. Then you sell that turbine to the US that have 60 hertz natural current. If they turn on that turbine, it goes perfectly in resonance. So it's not good to sell your turbines to the US unless you change the design. Okay? That happened actually with an American country getting turbines from the Soviet Union during the Cold War. They couldn't produce them, so they got, a South American country got turbines from Soviet Union. They were 50 hertz turbines, so with a resonance at 60, but they ran it at 60 because the electricity network was 60 and they had big trouble. Okay? Good. That's a good example. Now, let's take a break. That's just an example to let you understand why vibration is important. Okay. So I have received a couple of very interesting questions during the break. I'll start with this one. So if I have a force at, say, 10 hertz, is it possible that my vibration is going to be at 20 hertz or at 15 hertz? If I have a force at 10 hertz, force is shaking at 10 hertz. Is it possible to have a vibration at another frequency, 15 hertz? What's your answer? So the answer, according to what we've seen so far, no. And in most cases, the answer is really no. Okay? If your system is linear, so if your system actually has an equation of motion like this, which doesn't have square of y or weird stuff, nonlinear terms, you've seen nonlinear terms. If it doesn't have nonlinear term, no, you cannot have it, as long as the force is a sine wave, of course. If the force is not a sine wave, then you'll have a lot of stuff. Okay? But if your force is a sine wave, and it has 10 hertz, your vibration is going to be at 10 hertz. Maybe except the homogeneous part, but we know that goes quickly. Clear? So that's a concept that, to be honest, many engineers lack. It's really important. It's possible to have weird stuff when the system is nonlinear. And usually when you have a nonlinear system, what you get is multiples of that force, the force frequency. So if your system is nonlinear, you can have that if you force at 10 hertz, you can have vibration with components at 10, 20, 30, so multiples of that frequency. But only if the system is nonlinear, significantly nonlinear. If the system is linear, and many systems behave linearly for small displacements. Of course, if your vibration becomes huge, then the system is not behaving well anyway. But if your vibration is small compared to the dimension of the system, then you force at 10 hertz, you get 10 hertz in most systems. Clear? Good. So, again, when you have high vibrations, you have to look at two things. The problem could be in the force, if the force is too high. If the force is very high, this is going to grow. Okay? So, could be with the force. There's something wrong in your machine, it's very unbalanced. Your wheel of the car, very unbalanced, so the force is very big. But also, the other possibility is there's something wrong with your natural frequency. So your natural frequency is close to the operating speed of the machine. Okay? These are the two options. If they combine, well, it's even worse. If you have a big force working in resonance, it's big trouble. Okay. Any questions? Any more questions? Good. You're going to have next semester or the one after. I don't remember if it's first or second semester. Third year for sure. A unit called 321, Dynamics of Machines. Half of it is entirely on vibration. So you're going to have time to re-see this stuff much more detail. Okay? Good. Let's solve this exercise. I'm copying on my sheet. And we want to know the steady state vibration. Good. So what do? We draw the free body diagram. Forces. Try to draw the forces. Where do they go? Spring force, where does it go? Towards the center of the spring. And its expression is K delta L. Delta L of the spring. I'm going to call it delta L K just to remember the delta L of the spring. What about C? Force towards the center of the damper, C delta L dot of the damper. Then there is this horizontal force. I draw it here just because there's no space, obviously. F of t equal F0 sine omega t. Anything else? Gravity? Anything else? Reaction force. Very good. Or normal force, it's okay. Now write Newton's law in the horizontal direction where it's obviously relevant, mx dot dot equal minus k delta Lk plus c delta L dot c plus F0 sine omega t. How much is delta Lk? Is there any delta static? What do you think? No. If I want, I can try to put a delta L static and I will come out to be 0. But in this case, obviously, this spring, this system is in equilibrium when this spring is not loaded. So for delta static equal to 0, because gravity is acting in the other direction. So it's not making this spring longer or shorter. So this delta K is simply equal to, well, it depends, but in this case, let's say this is x. Delta K is equal to positive or negative? Positive, because it makes the spring longer. What about delta LC? Not delta L dot C, delta LC. So the length of this damper. negative x, because this damper is made shorter by x. So we are interested in delta L dot C, is the derivative of delta C, which is minus x dot. Is it clear? The time derivative of this quantity is minus x dot. Any question here? Now I'm substituting this thing in, and I obtain x dot dot. I'll bring those on the other side, plus C and delta L dot is minus x dot. No, there was a minus, sorry. Let's do it as it is in here. M x dot dot equal minus k and delta Lk is x plus C delta L dot C, which is minus x dot plus F0 sine omega t. I bring, this is obviously minus Cx dot, so if I bring those on the other side, I obtain plus Cx dot plus Kx equal F0. No. No. Sine omega t. Okay? Everybody agrees? Good. Now we found the expression. Now, m star is, what is m star in this case? It's everything in front of x dot dot. So m star is equal to m, which is 1 kilogram. C star is everything in front of x dot. In this case, it's simply C. K star is everything in front of x. So in this case, it's simply K. Good. So omega n is equal square root of K star divided m star, which is equal square root of 100 divided 1, 10 radians per second. Zeta is equal to C star over 2 m star omega n. Now C star is 1 divided by 2, m is 2, multiplied by 10, 20. 1 divided by 20 is 0.05 again. I think I did it right. Have we found the response? No. We were asked to find the steady state vibration and draw it. Now, I know that the steady state vibration, y, t, for t sufficiently big, yt is approximately yp of t, because yh is equal to 0, almost. And therefore, yt is equal approximately to a certain capital Y sine the same frequency of the force time minus a certain phase phi. And how much is capital Y? Capital Y is F0 divided K divided a big square root, leave a bit of space there, 1 minus omega capital divided omega n square square plus 2 zeta omega over omega n square. That's the formula you have on the slides too. Okay? let's calculate that thing. F0 was 10. K is equal 100. So 10 divided by 100, this is 0.1, the numerator. Denominator, square root. Of 1 minus omega. Said that the force frequency is 5 divided by omega n, which is 10, is 1/2, so 0.5. Square, close, square. Plus 2, zeta is 0.05, and omega over omega n is again 0.5, was it? Yes. Equal 0.1 divided 1 minus 0.25 is 0.75 square plus 0.1, this is 0.05 square. Now I need a calculator for that. That's 0.752. That's the denominator. And the numerator was 0.1, so 0.1 divided 0.7, or divided by that thing, is 0.133. .133 meters. Okay? So now we could calculate the phase. I don't bother, because I know it's not really important. If I wanted to be a very good student, I would calculate the phase too. Now I'll skip it. Okay, so this thing is going to be a sine wave. I don't know the phase, so I don't know how it starts. I can calculate with that formula on the slides. But I know that the amplitude, this value, is 0.133, and this is minus 0.133. And this thing is going to oscillate like this. Now, that's the steady state vibration. I know at the beginning something might be different. I know at the beginning there's something weird here. But after a while, the steady state vibration is going to be like this, with a period which is 2 pi over capital omega, because the frequency is now omega. So the period is 2 pi over omega. Omega is 5. So 2 pi over 5. (1.26 seconds). So it's a quite large vibration, 13 centimeters, but very slow. So imagine it's like, okay, that's how it looks like. Clear? This stuff, you can really visualize it in your head. This is 10 centimeters movement, so it's moving quite a lot. I mean, depending on the system, but it's a 1 kilo mass, so it mustn't be too big a system, right? It was 1 kilo of mass, so don't think it's a massive system unless it's made of feathers, okay? It's moving 13 centimeters back and forth with a frequency of with a period of 1.26 seconds. So it takes 1.26 seconds to go and back. Okay? Good. Let's say that this force changes frequency. Which frequency would you avoid? Which frequency would you avoid in this case? We are running now at 5 radians per second. Let's say this frequency of the force could change. Which frequency, say you are a vibration consultant, and they tell you, okay, I want to run this machine at different frequencies. Should I avoid some frequency, or can I run it whatever I want? 10 radians per second. I have to avoid stuff around this. So keep a bit of margin, okay, and tell them not too much close to 10 radians per second. Cool. Thank you very much for your lecture. It's actually the last year I'm teaching this unit. So it's been a pleasure. Thank you. And from next time, YT will start teaching. So he's a great lecturer, so I'm sure you're going to be happy.